Hi, so in this video we are going to learn how to use pKa values to predict the position of an acid-base equilibrium. So what you need really is the pKa values, and you need for the acid and the conjugate acid. And so you need to learn first to look at the reaction and figure out which partners in an acid-base reaction are actually the acid and which one is the conjugate acid, and which partners are the bases and the conjugate base. And then you need to find the pKa values that you can use to predict which side the equilibrium will favor. In general, recall that a higher pKa value now means a weaker acid. So let's look at the following reaction. We'll have T-butoxide reacting with water, and now we have an equilibrium where we form T-butanol as well as hydroxide anion. Okay, so now we look at this reaction and we need to first find out which partner is the acid, which one the base, the conjugate acid and the conjugate base. And you should immediately see that what happens here is that this green proton gets transferred from the water to the T-butanol in the product. That means the T-butoxide is the base, the water is the acid, the T-butanol is the conjugate acid, and the hydroxide is the conjugate base. Okay, so once you know that, next we can look at the pKa values for the two acids, the acid and the conjugate acid. So you can look this up in the pKa table, which I'll also give to you on the exam. So for water, the pKa is 15.7, and for T-butanol it's 18. Now the general rule is that an equilibrium will always favor the side which contains the weaker acid or conjugate acid and the weaker base or conjugate base. So in this case, where's the weaker base? It's the weaker acid is the one with the higher pKa. Okay, and so that's the T-butanol, it's the weaker acid, and the hydroxide is also the weaker base. So in this case, the equilibrium clearly favors the right side based on these pKa values. Okay, so you need to practice this skill with Skill Builders 3.4, please. Now, sometimes the pKa values of the acid and the conjugate acid are very, very different by many orders of magnitude. And in this case, what you have is more of an irreversible reaction than an equilibrium. So I just want to show you one such example. Let's see. Let's say we take this anion, which is a carbon-based anion, a very strong base, and we react it with water. Now what we will form is butane plus hydroxide anion. Okay, again I will color the proton which gets transferred in green. So initially the proton sits on the water and then it ends up on the butane. This means, like before, and so here's the arrow pushing for the reaction, right? This means that the carbon-based anion is the base, the acid is the water, like before, the conjugate acid is in this case the butane, and the conjugate base is the hydroxide anion. Now we can, once we know that, again we can write down the pKa values for the acids. We have pKa value of 15.7 for water and 50 for the conjugate acid. So notice 50, that's a super weak acid. Now this means you can now take the two pKa values, subtract them from each other. So 50 minus 15.7 gives you approximately a value of 34, which now tells you that there will be about 10 to the 34 more products than reactants. So this equilibrium favors the right side by about 34 orders of magnitude. It's really completely irreversible at the practical level. Yeah, so again, I would like you to practice this skill with skill bit 3.4 and checkpoint 3.12. Thank you for watching. We'll do some clicker questions tomorrow about these two slides.